Hi, this week we're going to be covering normal probability distributions. So let's get started. Alright, part one, we're going to be looking at standard normal distributions. Now, standard normal distributions are normal distributions. They're bell-shaped curves, and we're going to see that in a moment. They have a standard deviation of 1 and a mean of 0. In other words, they're centered about 0 and have a standard deviation of 1. We're going to use things called z-scores to figure out what our probabilities are, or use our probabilities to figure out what our z-scores are. And that'll make more sense as we go on. Alright, what does a normal distribution look like algebraically? It looks like this equation. Y is equal to e to the 1/2 x minus mu over sigma quantity squared divided by sigma square root of 2 pi. Now, it's better just to remember that it's going to be symmetric and it's going to be bell-shaped. This is the exact equation, but outside of writing it down explicitly, we're not really going to be dealing too much explicitly with that equation. But it is good to know what it looks like. Alright, so this is what a normal distribution looks like. It is often called a bell curve, or you can see that it is bell-shaped, and it is symmetric about mu, our central point. If it is a standard normal distribution, mu will be 0. Now, this is a probability distribution. So we're going to do a little bit of review over what a uniform distribution is. So if we look at a uniform distribution is not a normal distribution, but it is a probability distribution in the same way. Now, for a uniform distribution, the area under the graph is equal to the probability that we are looking at. And so the total area under our graph would be expected to be 1. Same thing with a normal distribution. Normal distribution, the area under that curve is equal to 1. And that is one of the reasons why we have many of these less than clear coefficients here. Square root of 2 pi, for example. Alright. Now, for a uniform distribution, the probability density is going to be the same everywhere. And we're going to look at a rectangle here. You can also look at triangles as well. They won't be uniform distributions, but they'll also be probability density curves that one can calculate. Alright, so uniform distribution, in other words, the probability density is the same everywhere. And the area under it is equal to 1. Alright, so let's take a look at an example. And this is just going to look like a rectangle, and we'll see that in a moment. During certain time periods at JFK Airport in New York City, passengers arrive at a security checkpoint have wait times that are uniformly distributed between 0 and 5 minutes, as illustrated in the figure on the next page. Alright, so that means the probability of waiting any amount of time is exactly the same. However, you'll wait no less than 0 minutes, and you will wait no more than 5 minutes. And all of these probabilities are equally likely. Now, the thing about a probability density curve like this is that your probability of any exact time is going to be 0. Because the total area, and the area is what your probability is, the total area is 1, meaning that you will definitely wait between 0 and 5 minutes. However, your probability of waiting any exact moment, say exactly 1 minute, is going to be 0, because the area of the line directly above 1 right here is going to be 0. All right. And this is what it's talking about. Any time is possible. So 1.23456 minutes is possible, but the probability of that exact time will be 0. our height here, we want the area to be 1, so 5 times what is going to give us 1? 5 times 0.2 will give us 1. So a uniform distribution, that's how we will figure out what the density is. You want the area to be 1. Same thing with the normal distribution. You want the area to be 1. Alright. Given the uniform distribution listed in the figure, find the probability a randomly selected passenger has a wait time of at least 2 minutes. Now, at least 2 minutes means we are going to look at the area from 2 to 5. In order to illustrate that, let me go here, and what I'm going to do is I'm going to actually insert a shape. And so this will give us an idea. So between 2 and 5 minutes. So that area there is our probability. So we have 1, 2, 3, and 0.2 here. So our probability should be 3 times 0.2, which is 0.6. So our probability will be 0.6. Area 0.2 times 3. Right there. Now, if I were to say, and let's go back up here, if I were to say a wait time between 2 and 3 minutes, probability would be 20%. 2 and 2.5 minutes, it'd be 10%. 2 and 2 minutes 15 seconds, 5%. You see that as this gets more and more narrow, that probability becomes less and less. That's one of the reasons why I said if it's an exact time, our probability will be 0. So let's continue. Alright, so our standard normal distribution. Standard normal distribution, as stated before, a mean of 0 and a standard deviation of 1. The total area under the curve is equal to 1. Now the z-score is this value down here. 0, 1, 2, 3, -1, -2, -3. The z-score is simply how many standard deviations from the mean that the particular point you're looking at is. So z-score of 1 would be 1 standard deviation above the mean. The z-score of 2 would be 2 standard deviations above the mean. So how do we find the probabilities of the areas? Now note, I was able to draw a rectangle when we had the uniform probability density. Here I can't quite do the same thing, mainly due to limitations in Microsoft. But I can still say what is going to be my area from, I could say -infinity up to 0. Now I know that my probability from -infinity to 0 is going to be 0.5. The reason I know this is because I know that the standard normal distribution is symmetric about 0. That means half of my area is going to be below 0 and half of my area is going to be above 0. But the other numbers are going to be a bit more difficult. And the way we do that is we can look at certain tables, and these are called z-score tables. One should come in your book. That would be table A2. You can also use technology, and we'll be going over both of those in this lecture. If you don't have the book, or you have another book, you can also just look up z-score chart PDF. That's what I did, and I was able to download a table that we're going to be looking at in a moment. Alright, so if using A2, understand our probabilities are always going to be between 0 and 1. Probability can never be negative, but we can have a negative z-score. If our probability is less than 50, then we will have a z-score that is negative. And when I say probability, I mean the probability that we have a value less than that z-score. So cumulative area to the left, this is normally what a Z chart will show us. Up to Z, what is the probability? In other words, what is the area under this curve? We can also try to figure out what is the area between two boundaries, a lower boundary and an upper boundary. We'll be looking at doing both of those. Let's take a look at the example given here. The bone density test. Right? A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a Z-score. The probability of a Z-score is normally distributed with a mean of Z and a standard deviation of 1. So the test results meet our requirement for a standard normal distribution. And as we'll find out later on, as long as it's a normal distribution, we can still change it to a standard normal distribution. Right. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score of less than 1.27. So we have a Z-score that's equal to 1.27. And we can go over to our Z-score here, and I've already highlighted it. 1.2, that didn't work. 1.2, you can look here, you just go over. 0.2 is going to be one of these, and 0.07. So 1.27, we want to find out where those two intersect. So they intersect right here. 1.27. 0.8980. So our probability of getting a scan below 1.27 is going to be 0.8980. If I wanted to know my probability of getting below a 0.88, so I'd go up here to 0.8. See 0.8 here, 0.80, 0.81, 0.82, 0.83, 0.84, 85, 86, 87, 88. So that would be an 81.06% chance, or 0.8106 probability of getting a 0.88 or lower score. That's where we get the 0.8980. What if we want to use Excel? So again, we're looking at the number Z is 1.27. So let's go over here to Excel. Well, I have a couple of Excel functions here already. Normal S distribution, normal S inverse. So S, notice that these two functions I have right here have an S in there. That is because they are standard distributions. So the probability of Z up to a certain point. So let's take a look at that. What is the probability that we have Z less than 1.27? That is going to be equal to, and I use this probability up to Z, is equal to NORM dot S, don't forget the dot S, dot DIST 1.27 close parentheses. I have not entered two few arguments. How many maybe? 1.27, sorry. Comma, true. You'll notice that there's this cumulative here. That cumulative for us will always be true. That just means the probability up to that point. So 0.897957685. So it gives us a little bit more digits. A few more digits. So that's how we can use Excel for that. And so that's going to be our shaded area here. Now, figured out what the area was to the left. 0.8980. Again, multiply it by 100 to get our probability or our percentage. So that means 89.80% of the people with a z-score below 1.27, or will have a z-score below 1.27. 1.2 all the way over, 0.07 all the way down. And so that will give us exactly what we talked about. 0.27, 0.89. Okay. Take a look at this other one. Bone density test, finding the area to the right of the value. This is what we did last time. Or no, this is opposite of what we did last time. We found the area to the left. Now we're going to look for the area to the right of the value. Using the same bone density test, find the probability that a randomly selected person has a result above -1, which is considered to be the normal range of bone density test. So, above -1. Now, due to symmetry, you could also say this is the probability that it is below +1. But we'll go ahead and look at the probability that it is above -1. Now, in order to figure out the probability that it will be above -1, we need to find the probability that it's below -1 and subtract that from 1. Take the area here, 0.1587, subtract that from the total area under the curve, which is 1, and that gives us 0.8413. So again, we can use the z-scores. Here, I'm going to go to the first page I got here, and I'm going to look at a z-score of -1.1587. All right. So we have 0.1587. Now, some charts will have this the opposite. So it'll start out 0.09 and then go down to 0.00. And I believe that's what we have in our book. So do be aware of that. Make sure that you're actually looking at the right one here. So we're looking at -1, so that's 0.1587. And that gives us what they find here. 0.1587, subtract that from 1, we get 0.8413. Now let's try to do that in Excel. So let's go back here. We want this to be -1. We're going to do 1.00. Actually, we're not looking for less than, we're looking for greater than, because we want it to the right. So this one, instead of saying equal to the norm of the distribution, I'll say 1 minus the normal distribution of -1. Now we get 0.8413444746. Again, we get more digits. So that's good. And we find that with technology or using the table, we should be able to figure out what our probability is. All right, what about a bone density test between -1 and -2.5? All right, so now we're going to figure out the z-score to the left of 2.5, or -2.5, and to the left of -1, and subtract the two. Again, we could use the chart, the A2 chart, and we would get that. The area here is equal to this area minus this area. And it's saying we have 15.25% of the people who have this issue, osteopenia, which is a bone density issue, which I believe is slightly better than osteoporosis. I'm not sure. All right. So between any two scores, we shall simply subtract the two. This makes sense. We have the area is just going to be the difference in the two areas. Now, what about if we want to use Excel to do that? Well, I can say what is the probability that we have negative 2.5 less than z less than negative 1. And that is going to equal, again, I'll use my normal distribution, and I'll just subtract two normal distributions. S dot dist negative 1, comma, true, minus norm dot s dot dist negative 2.5, comma, true. 0.15244. If we look here, we get 0.152. Well, in that case, we got 5, but we got 244, and then 5589. So, a similar answer. That's what we got here. So I've been using this notation already, but this is just showing us a notation if we want to have the probability between two values, A and B. We just denote it as A less than Z less than B. If we want Z to be greater than A, we denote it like that. If we want it to be Z greater than A, if we want it to be less than A, Z less than A. Critical values. For a standard normal distribution, the critical value is going to be a score on the borderline separating these scores that are significantly high or significantly low. And these would be denoted Z alpha. And that is, we're looking at the areas that are super small, or sorry, relatively small and relatively low. And your chart out of your book should also have these Z-scores, common critical value scores, I should say. Z of 0.025 would just be Z of 0.025, sub 0.025. And it's the area that's here and the area that's up here. If we subtract both of these areas, 0.025, 0.025, that's about 5%, meaning the area between these two will be 95%. So, indeed, the probability between these two is simply equal to 1. Probability is equal to 1 minus Z of negative 1.96. And, of course, we have the same area here by symmetry, so we can actually subtract 2 of those. All right, so what do I mean by that? Well, let's go over here. So the probability is equal to 1 minus 2z of alpha. So that means 2z of alpha is equal to 1 minus the probability, or z of alpha is simply 1 minus p over 2. And we'll get to this equation in the next lecture. But for now, this is what we're looking at. So the probability, if we want to have a certain probability, we want to have 50% of them between a certain amount, we can use this to figure out what our z-score would be, or what we would need to get to read. We'll go back to redundancy test. Yeah, there we go. All right. And that is the end for the first part. And we shall continue with real applications of normal distributions. But we have 25 minutes of lecture, so I will go ahead and leave that for a later time.